Problem, we are given the question, in a particular population of finches, short beaks are quite common. The allele for short beaks is recessive to long beaks. The frequency of short beaks is 0.75. So again, let's stop right here and think about what we're given. The frequency of short beaks. Is this an allele frequency or a phenotype? This is a phenotype frequency because we're told that the individuals have short beaks. So we're going to use that information to calculate the allele and genotype frequencies within a population. So if we are given short beak frequency, that means we are also being told the homozygous recessive genotype. That corresponds with Q squared. So Q squared is going to be equal to 0.75. Let's use that to calculate Q by taking the square root of 0.75. So Q is going to be equal to 0.87. This is the frequency of short beak allele. Remember that Q squared was the frequency of the short beak phenotype. All right, so let's now use Q to calculate P. So P plus Q equals 1. Therefore, to determine P, we're just going to use 1 minus Q. So P is equal to 1 minus 0.87. P is equal to 0.13. This is the frequency of long beak allele. Now, the other part of our question is to calculate the genotype frequencies. So let's put back our equation. P squared plus 2PQ plus Q squared equals 1. So we were given Q squared. So the genotype frequency of short beaks, which is Q squared, is equal to 0.75. So we already know that. We don't have to calculate that one. But we can calculate our other genotype frequencies. So remember that the genotype frequency of the homozygous dominant is your P squared. So P squared is equal to 0.13 squared, which is equal to 0.02. This means that 2% of the population are homozygous dominant with the long beak phenotype. Let's then calculate the individuals who are heterozygous in our population. This corresponds to 2PQ. So 2PQ, our heterozygotes, are equal to 2 times 0.13 times 0.87, which means that 2PQ is equal to 0.23, or 23% of the population are heterozygous carriers for the short beak allele, but they are displaying the long beak phenotype. Now, let's use this to determine whether or not evolution is occurring. So, after a drought year, the finch population has a short beak frequency of 0.65. So, in our last problem, the short beak frequency, or the Q squared, was 0.75. In our new population, Q squared of the new population, our frequency is 0.6. Our genotype frequency has changed. This means that evolution has occurred. If we look at the Q value of our previous population, Q is equal to 0.87. The Q value for our new population was 0.6. Excuse me, sorry, I forgot to write this one down. The square root of 0.6, which is 0.77. So we can see that this has changed just a little bit. Not a lot, but we could use some different statistical tests to determine if this is a significant difference. But we will just go ahead and assume that because Q has changed, evolution has occurred. So let's think about which of the HardyWeinberg assumptions has been violated here. Because we're in a drought year, you can safely assume that the environment has changed. So we have an environmental change. This means that very likely natural selection is acting on this population because one trait is more advantageous than another in this particular situation.